briefly review kind we have learned in the graph algorithm. And also, you see we have web page list all the important materials and also videos, right? And so currently, we talk about the graph algorithm. The graph, it is a connection of complex related data, right? This is the definition of the graph. And then so have different representations. And we talk about adjacent list and adjacent matrix. And both used to emphasize how to represent a relationship, right? How to represent this relationship of data. And this is the different method. And after that, since the graph, we know that the graph, they allow the cycle, right? They allow the cycle. For example, right? And in that case, it is when we want to walk through all the loads, and we want to make sure they maintain some order. So this is what we call about the graph traversal. Corresponding to you walk through the graph and to visit each guy, do something on each guy. So this is the graph traversal. And in graph traversal, we talk about BFS and DFS. And this implementation is quite intuitive, right? Which is based on the tree BFS and DFS. What they updated, it is they add up the variables to use to represent the status because they don't want this cycle go around and around, right? They need to avoid the cycle, right? Extend, which is extend the tree traversal, right? Extend the tree traversal. So this is something we need to remember. And then so once you understand the tree traversal, because they use recursion, right? And then so it will be easy to understand, right? And then so now let's take a look. And then another question, very important question, which is the reachability question. Corresponding to, we see here, this edge just corresponding to this vertex 1 and this vertex 2, they have a relationship. This vertex 1 should be, cause something to the relationship, this B, this 2, right? But, and this just say step 1 relationship. The edge corresponding to the step 1 relationship. Why we call the step 1? Why we call step? Corresponding to just one jump, and this guy, this load can link to this load, right? Just one step they can link to. This is step 1, neighborhood relationship. And then, so with reachability, it's not about only who is connect with which one. Reachability corresponding to this vertex 3. Can 3 reach to 2 or not? Can 2 reach to 3 or not? Right? And when we talk about reachability, we talk about step star neighborhood. This star could be 1, could be 2, could be 3, could be 4. Could be, if we have n nodes, could be n minus 1. But not beyond that, right? So you want to check reachable, this is 3, can reachable to 2, this one can reach to 2 or not? Well, 2, in this case, right, is 3, the vertex 3 is reachable to vertex 2, right? Or people ask, is vertex 2 reachable to vertex 3? And so this is reachability problem. Reachability problem, and you can use different solution for that. BFS also related to reachability problem, right? Because once you go from the source and level by level, you reach the loads. And also DFS could be. Another thing it is, people not only care about the step n neighborhood who can be reached to. they also want to make sure the shortest distance reachability. Corresponding to, they want to find out for any vertex I to any vertex j, what is this shortest path? Corresponding to what? They want to find out the most efficient star prime. They want to find the efficient star prime. They want to find the minimum steps. Minimum steps such that Vi is reached to so the minimum step Vi reaches to rain. This is a review. This is a more intuitive review. Reaches to rain. Anna? Yes, I want to make sure you pay attention, okay? And then, so this is the minimum step such that Vi is reached to Vj. This is the people care about. Another thing it is, so since we talk about shortest distance, right? Another thing is people care about minimum summarized weight. This is corresponding to the path weight. The path weight, right? And the path weight, minimum of this one, and such that there is a path, a shortest distance path from Vi to Vj. This is what we talk about in this week. Now, I want to give you even more intuitive idea, right? So this is, you can say, this can be derived to different job interview question. If people ask you only reachability, do not care about the distance, you do not need to care about this one, right? You just check how many steps could be. And then corresponding to, you put the weight as 1, right? So all what we learned this week, you can derive to answer different kind of questions. Can you see that? Let's go to reachabilities. That is the question for what we discuss. All these algorithms we use. Now I want to give you even more intuitive idea, right? So in this module, in the very beginning, we follow slides. We talk about 2 optimal property. I use different color to represent that. So we have optimal structure property corresponding to this property. Corresponding to what? We say every time, if you from V to U is the shortest path. If this is the shortest path, then we say in any point here is T is here. And we can make sure this is also shortest path. This is also shortest path. This is the optimal structure. Corresponding to all the shortest paths, it consists of, you can see recursive definition came from here. The shortest path, to save my time, right? I use SP to represent the shortest path, right? SP corresponding to shortest path. Okay, so the shortest path of U to V is equal to the shortest path S to T plus shortest path from T to V. From U to T. right? So you can see this recursive definition. Can you see that? Yes? Pedro? Okay. Another definition, another specific property, what we talk about, we use a lot in this module, which corresponds to triangle inequality. And also related to this one, we talk about that it is if we have U, let's say put them together, right? If we have U to V, we see here, we see U to V, right? This is what we found out, shortest path, right? SP. And for some reason, we have this one, we have another vortex T connect with V, right? And from U, this guy, right? So we see that here, the shortest path, if you find out this T1, right? If you also have T2, this T2, all these corresponding to, they have T3, right? So for some reason, they do have a reachable from U can reach to T1, U can reach to T2, and U can reach to T3, right? So the shortest path of U to V is equal to what? Let's make it even simple, right? Let's make it simple. I delete that. I make a edge connect that. And I put a weight here, right? And this one do have weight, right? So this is T1 to V. This is the T1, T2 to V, right? Let's say we have a multiple vortex connected with U. Then the shortest path of U, from U to V is equal to minimum, right? Based on what we discussed here. Right? Is minimum of what? Is minimum of if they do have a direct connection of WU, right? Or let's say we use T to represent the adjacent vortex of U, right? This is adjacent to, I use adjacent to. Corresponding to T1 is tilde this guy, right? And this is for direct graph. For indirect graph, corresponding to, we draw it this way, right? This is V, this is U, and this is what we have T1 and T2, right? And you could have more. You have TK, right? And this guy is linked with this guy. And they do have reachable from this guy, from U, they can reach to any of these kind of things, right? And then they have direct edge from TI to V, right? To V, right? Let's say T in the direct graph and T is a vortex, is belong to, we use ADJ to represent the adjacent vortex of V, right? Clear? Okay. And then, so we see here, doesn't matter which case. And SP is equal to minimum for S1 and what? And because they need to choose the shortest one. This is reachability, right? First, this guy, they should be reachable, this guy, right? It should be reachable. And then you consider shortest path, right? Shortest path optimization problem. They minimize this one and also minimize for any T which belong to adjacent V, and we have shortest path from U to T plus W from T, the weight, right, to V, right? So the whole thing here, this is the function for shortest path. Can you see that? And then, based on this function, people got a different algorithm from the different perspective. And This is clear, right? Yes, good. And then yes, adjacent list. This adjacent 2 for direct graph, right? This ADJ corresponding to adjacent, corresponding to next to, right? Corresponding linked to, right? It's clear? Yeah. Okay, good. That's good. You ask a question. That's good. So every student, if you feel you want to ask a question, you just BB and raise your hand. I can put you on mute. Okay, good. And then so now we go to the algorithm perspective, right? You can see this is the recursion, right? Can you see recursion? And this function got to invoke, and this function will use the this function, can you see? And this is function, right? This is recursion. And if it's a tree, easy, they will be good to do. Now it's a graph. The graph become very tricky. Why? The reason it is, and from this U, you go to the V, and for some reason, you have T, you go back here again, and then you go back here again. They have a cycle. If you have a cycle, you correspond to, just give you one simple example, right? So you from U to V, and this one, then you go to this one, right? This is a cycle. In that case, it is U to V, and then still U to V, right? And T could be something, let's say use this way, right? 3 nodes, right? 3 nodes. And 3 nodes, this one, and you go back to here, right? So once you have the cycle, in this case, it will be recursion forever. Or you have something is not well defined, right? So once you have recursion, this is not good. Maybe happen these undefined things, just like we talk about, for negative with a cycle that is not well defined. Or since you have recycle, maybe the calculation will be duplicated. Right? So it means the algorithm perspective only use recursion, not a good idea. With recursion, you can write very easily, but not efficient. So this is go to the algorithm, the digester algorithm. This will go to the review the question, this one, right? Digester algorithm, and this algorithm which is use greedy, what is idea? So corresponding to, since you wanted to pick up the shortest path for this one, right? So it means every time you want to find the shortest path, and such that digester this scholar, they think about, since this is the optimal structure and the shortest path consists of shortest path, right? And such that, so this is go to the greedy algorithm. So this is also the review of the algorithm, and currently we have none so far. And this is go to the greedy algorithm. And the also think about, since your shortest path included the shortest path, so everything here should be shortest path, right? Everything here should be shortest path. And just note, also think about, let's make each step here is optimal. Each step here is optimal, right? And so this is digester algorithm. So this is also single source. It is starting from very beginning, the source node, single source shortest path, right? And corresponding to give you the graph is S, and then you want to check what it is the best way to for example, right? Let's just give you example. And then, so in that case, they have loads, have weight, they have weight here, right? Each edge, they do have weight. And then, so you follow this algorithm corresponding to every time when you explore, you want to make sure this is the shortest path. For example, right? I just give you example, since here is already, we already discussed about that, right? So you're starting from S. Based on the weight here, you choose the shortest one to go, right? And so go this is the shortest path. And then go to this shortest path, you check the adjacent vortex. You say, okay, this is adjacent for this 2, and then you choose the shortest path. From here, you go explore. Every time the level-based exploration, you make sure you give the shortest path for every new explored vortex. Is clear? So this is very similar to just think about the BFS. BFS exploit out, right? This one is the BFS propagate. W represent weight corresponding to distance, corresponding to, for example, for your home to the UNCC, how many miles you need. It's weight. People use this weight to represent different things. Or the confidence. From this one to that one, this interaction, how confidence could be for the course project. Right? So this is a BFS propagate-based optimization. You propagate out for each level. When you propagate in this level, you find the optimal shortest path. Then you go to the this level, you give the shortest path. Then you move to the third level. It means your step 2 relationship, step 3 relationship. Then every time you readjust this one to make sure, so when you explore, you get the shortest path. It's clear? Because every time you want to make sure you get the shortest path, right? It's clear? This one you go to take a look at algorithm. So you just say if you still have concern about that, you go to the PowerPoint. You go to take a look at the algorithm. This algorithm is very typical algorithm. It's greedy algorithm. The most important to understand one algorithm, first you need to know what is intuition. What is the problem there? What is intuitive design? And then based on this intuitive design, then you know how to solve this problem. Then you go to take a look at the algorithm. Then you go to take a look at the runtime. So on this digester algorithm, I want to get it maybe not easy to move. It's just a very slow computer. Okay, so let's see. Okay, let me write it down here. Okay, good. Okay, I briefly write down the algorithm here, right? So, first initialize. So in this algorithm, they have a weight for each loads. They use the D to represent, DU is represent the shortest path. We know what the load shortest path corresponding to, right? Corresponding to weight, the total weight on the path from S to U, right? This is definition. And also we have U, this one to represent the parent load in shortest path. Corresponding to this value corresponding to pi U, which this is the U, which is belong to this edge, right? This E, which is belong to the capital E, for example. Okay, so the first step, initialize that, make sure every one, it is in infinity, right? Initialization is a for loop, right? For every, I use this one to represent for every V. Just simplify that, right? Simplify. Maybe this is not a good way. For every vortex, right? Use V belong to, I use this way, belong to V, right? So you have du dv is equal to infinity, and also you have your pi, and this V is equal to long, right? So this is for utilization step. And then second step, since you wanted to pick up the minimum guy, so we use the priority queue. So we use a priority queue, right? So initialize priority queue. Corresponding to, let's use PQ to represent that. So corresponding to every this load, so you have this all this object is already here, right? The value is here, right? And then, and also you sign this one, you sign ds you sign the ds to be 0. And then, so initialize the priority queue. Hello? Good? Good. And then, so the third step, right? The third step, it is you want to propagate and greatly, let's write it down this way, greatly propagate to adjust the shortest distance, this d, v for every guy, right? Greatly propagate to adjust dv, right? Because finally you need to find for every this v, right? The v is belong to, for any this kind of v, belong to v, right? Okay, so how can you greatly to do that? You see, well, the PQ is not long, it's not empty. And then what you do it is, you remove vortex, right? You have U got to move out and remove the smallest one, minimum D U from this guy, right? So if corresponding to, you find the minimum of this guy, right? Find the minimum of this guy. Remove the minimum of the only this kind of vortex, right? So, it's clear. And then so you get this guy. Corresponding to, you get the very beginning, this guy. Then, so after that, it is you retrieve this one through this guy, through the smallest one, right? And from this one, find the smallest weight. So how do you find the smallest weight? That will be good to this way. So you see for any, let's say this is U, right? This V belong to adjacent U, right? You check for every vortex in adjacent U. This is U, this is U, right? This is adjacent one. So then what you do it is relaxation. Relaxation corresponding to, you say the dV is equal to minimum of dV, or the du plus the weight uv. You get the minimum one, right? And then so at the same time, you adjust this pi v based on is equal to u if dv, this dv you can prime, right? Because this is new value. It's different from the what you have the previous one, right? And then so of course, what you have the dv is equal to d prime v. So this just say to make it clear in your side. So in this one, in the algorithm, they just use the relaxation. It's same as relaxation. And then so after that, so in this way, you adjust. You adjust the distance, the shortest distance. In such a way, you change this this priority queue, right? And such that the next time when they remove from this priority queue, they remove the vertex which has the shortest distance. The next one who had the shortest distance in the remaining priority queue. This is the gesture algorithm. And the idea here, it is based on the shortest path, which include the shortest path. So they want to make sure every time they want to propagate out, all this one is the shortest. This is shortest path, is the shortest path, and this is also shortest path. This is the gesture algorithm. Can you see? Very clearly, right? And then another algorithm, this is we'll talk about the Bellman algorithm last class. I finished that in the end of the class last time. This use dynamic programming. I want to use this one to explain to you. This is a very intuitive explanation, and from the mathematics and from the computational algorithm design perspective. And once you understand this intuitive, this design, writing the code is so easy. And so now the Bellman we think about, right? I'll go back here. So another way, it is this one, right? Still go to this SP, this recursion. And this recursion, take a look at this recursion, right? And so this recursion, the two vertex, if they are reached to each other, the shortest path is equal to the minimum of this one plus the another one. Corresponding to this plus corresponding to the next step, the another step neighborhood, right? You jump a little bit more. Another step of relation code, and such that this one can be reduced to the problem like this one. SP, you treat this shortest path between any vertex and V as a matrix, right? This corresponding to matrix. And corresponding to matrix of all these vertex here. Let's say this is V1, V2, and this is Vn. And this is V1 and go to the Vn, right? So let's say this is what we have the U, and this is what we have the V, and such that this value corresponding to the shortest path of this one. Or if you just take a look, the first step one relationship, right? If it's step one neighborhood relationship, this corresponding to, this is the SP0, right? SP1, let's use SP1. SP1, this corresponding to the weight. And SP2, UV, corresponding to the shortest path. This is step 1, right? And this one corresponding to shortest path in step 2 neighborhood. Right? And so this one is equal to what? Is equal to the minimum W. Okay, let me use another way to represent. This is equal to, very interesting happen. This is equal to SP1 UV, right? And or SP1 U to T plus T. No. U to T, right? Plus what? SP1 T to V. Can you see that? This is the idea of Bellman's algorithm. Okay, I think this is fine, yeah. Okay, so you can see this is the Bellman's algorithm, And the Berman's algorithm, you can take a look at this one, right? This one, right? And you see this is just a step 2 relationship, right? Step 2 neighborhood. Now the Berman say, the author of the Berman say. So what do you have? The t+1 step relationship of UV is equal to minimum of SPT UT plus SPT T to V. And you can say, right? And then, so even for here, you can use recursion. This is the SPT UV, the previous step, right? So this is the for the T step neighborhood. And then you can observe that, right? You can observe that. So now let's go to the algorithm very quickly now. So, and then how can you represent this as PUV? Because it's matrix, right? So you have this matrix, which is a step 1 matrix. And then you have another matrix. So you have another matrix. This matrix, which is a step 2 matrix. Same thing here. It's V1, V2, and Vn. And V1 and Vn, right? And so you can see to get this value, to get what you think about this guy. This one, right? This one. And this one, this value, let me write it down here. I use a different color to represent. This one is equal to, I use another color to represent this matrix itself, right? This is V1 to Vn. And this is V1 to Vn. And I use multiplication to represent that. This value is equal to, I use this color, corresponding to this U, this line, right? Times this line. And this line corresponding to U to each this guy. V1, V2, and Vn. And this guy is equal to this guy, right? The different rows correspond to different V1, V2, and the Vn is equal to V, right? This is U, this is V. And corresponding to this is V, right? This is V. And then, so we say we multiply them together. This is a specific multiplication, and this is an overload application. Corresponding to, you check this one, check this one, check this one. You get all of them together. You use, since this is Boolean, right? So you can use you can use what? Use OR relationship, right? It's OR relationship, and this is exactly go to the here. To say from U can reach to V through any intermediate, in the middle, some middle vertex or not, right? If you from here, you do have a better solution from here to here, and from here to here, in that case, this is the value you calculate for this guy. It's the two-step relation. It's a two-step relation, right? Two-step relation corresponding to, you have this adjacent matrix times this adjacent matrix. Now you can continue to do this one, which is go to the what you have the n-1 step relationship hood, right? And based on this concept, so you could have an algorithm very similar to, this is the Bernoulli algorithm. You use a for loop. So you say for, of course, initialize, right? So initialize SP matrix. And SP matrix is exactly adjacent matrix, right? And has the weight is adjacent matrix. And then what you do, it is you need to time this one by itself. And you need to time this one for n-1 time, right? So you have a count variable I from 1 to n-1. You want to repeat this one for n-1 times. And inside of this one, it is for any vortex in V1 in V. And any vortex, let's say you use U to represent, for any vortex in U, right? This one in the V in the V. So what you do it is you do the matrix multiplication, right? Multiplication. Did you see that? So in the matrix multiplication, you have this one for T, which is belong to the something in the middle, right? Still V, right? Then in that case, you have SP UV equal to what? Equal to, you can use mean SP UV and SP UT plus SP TV. Then, so this is the algorithm. You finish just like that. And in the Berman, they also do one more step. And then this step is used to what? Used to check another step. Once you finish this one, this algorithm should is pass finish. Another step is check the negative. This one is to check negative weight cycle. Which one? I think it's time now. Okay, what is the question? Wait. SPUV? This one? Okay. Let me finish this one, Rain. Let me finish this one. The reason it is many students, they may need to leave very soon. So it's almost is the time to release class almost now. Page rank maybe we move to some another time to check. So I copy this one, and then so I paste here, right? Paste here. I paste. Let's see, can I paste it? So I paste here. Also move it a little bit down. So the whole thing here, what they do, and also remove this one out. And so the whole step here is used to check negative weight cycle. So this is if, I think this one we have another for V, for U belong to V. So, okay, this is capital V. Okay, so then here they change this one. They say if this one still smaller than if this one still smaller than this one, then in that case corresponding to it return true. Corresponding to they do include negative weight cycle. So depending on the question people ask you, if we just want to get the shortest path, this one is good enough. And also keep in mind, you need to change the pi. So the pi here, and you need to change the pi, right? Corresponding to change the pi, right? And then so you finish this one. This is another step. You want to check if it include negative weight cycle or not. And then so what else it is, if there's nothing here, is not return in the middle. In that case, that doesn't include the negative weight cycle. Then so we give you very detailed discussion for this, the algorithm here. And you can find out this the second solution, which is the dynamic programming. Because it's starting from smaller, step 1 neighborhood, step 2 neighborhood, step 3 neighborhood. It's starting from the smaller until step K n-1 neighborhood, right? So this is dynamic programming. So you can see the graph algorithm, all the technique we talk about in this semester, actually also used for the advanced graph structure. And also the algorithm, people name us the advanced algorithm, but actually still not beyond the technique we talk about in this semester. You just say think about things, since that is graph is advanced data structure, and then how do you measure this shortest path? How do you think about this shortest path? How do you think about reachability problem? So okay, I think that is give a very detailed discussion about this one. We finished this module, and so for minimum spanning tree, that is something we can check next Monday. Okay. And then it's also page rank. Page rank is usually this kind of advanced topic. And I think this part, yeah. Okay, this one you just follow what you have here. Let me take a look. Oh no, not this one, right? Did I erase something? No, not really, right? Okay, that's good. Okay, this one is released. Let me write it down. So this is SPU to T plus SP T to V. Okay, this is the plus sign. Okay, so this is for the shortest path. Okay, I think I finished the run and then run. Okay, good. Yeah. Okay, that's good. Yeah. Okay, and then so for the page rank, I plan for to discuss about that. So definitely I will discuss about that. Actually, it's just continue because you may find out they use the same kind of the strategy. They use the same kind of strategy, and for page rank, it's just see the problem. They check the importance of each node, and they use the adjacent vertex as the contribution, and to check the voter support. And algorithm is very similar to what we discuss here, and use iteration. So here, take a look, right? So we see the recursive solution has been replaced. Replaced with iterative solution. And so that is the page rank. Iterative solution. In this shortest path problem, this is kind of, okay, in the shortest path problem, use greedy algorithm and dynamic programming. And in the page rank problem, they exactly is the iterative solution. And it's very similar to what we checked here. It's very similar to the dynamic programming approach. So since page rank is not in the curriculum, so I will try to spend the time on that and give you a discussion. And in the remaining of this semester, next week, we'll finish minimum spanning tree. And this is also a good thing to check, and which is used just like a propagate. And once you know this algorithm, the greedy algorithm, dynamic programming graph algorithm, to learn that one, it becomes very easy. So next Monday, I finish minimum spanning tree. Then I want to go to the NP hard problem, NP problem, NP complete problem, NP hard problem. Then we go back to check the page rank. Then we go back to check how can we use linear programming to solve this NP complete problem. Okay, then we'll finish. So the NP complete problem, which is in the curriculum, and this is the use just one or two class we finish. So it's a short module because it's just from the theoretical part to discuss the different problem categories. And it also answers the question that any problem can be efficiently solved in the polynomial time solved. This question we asked in the very beginning of the class. Next Monday, at least next Wednesday, we need to go to the NP complete. This the problem classification side. And then so the Friday, I would like to move to the linear programming to see how can people use linear programming, get approximation algorithm to get approximate results. Okay, use linear programming. Then so the page rank I was trying to afford that you squish somewhere next week. Okay, I already prepared for the page the page rank. Once we finish this one, even in your site, if you read the slides, or I already post the slides in the canvas, and then you can also get that. It's just seem some students they have to leave, and actually I really would like to go and take a look. It's easy, just one thing, and I check. Just one thing I wanted to to tell you, the formula. Once you go to the formula, then you can see the algorithm solution very similar to what we discussed today. Still, it's about the recursion and how to make the iterative solution based on this recursion. Okay, so I think that is the time now. I think I'm maybe not so good, because some students have to go. So not good to hold this one to give you push this page rank. This was not supposed to be in curriculum, and I push this concept, push this algorithm to you. Let's say we squish this page rank algorithm next week. If it is not next week, then we go to the next Monday or next Wednesday. So next Wednesday we will have one more session, okay? So which is reading day, but since it's remote session, and I would like to use that time to answer a question or use that time for review, okay? So next Wednesday we will have one more class. So it means after today we have 5 classes left. Okay, so I think that's all. And evening 8 p.m. So we will have the discussion for paper 8. And tomorrow, 3 p.m., we'll have the discussion for paper 10. Okay, this is based on student request. If you do not request that, I will suppose not. If you no request from the team, I will assume you have no problem with your team. Okay, so I think that's all for today. Okay, I think